Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is the part of the Steps into Complex Numbers series and concerns Argand diagrams and polar form. This guide introduces Argand diagrams which are used to visualise complex numbers. It also shows how to calculate the modulus and argument of a complex number, their role in the polar form of a complex number, and how to convert between Cartesian and polar forms. Introduction. One of the problems that mathematicians came across when they were exploring the idea of complex numbers was their visualization. A complex number does not appear anywhere on the real number line, and so it would not appear in coordinates in the xy plane. This problem was solved in an ingenious way in the 19th century by Jean-Robert Argand, building on the work of Caspar Wessel. An Argand diagram uses the real and imaginary parts of a complex number as analogues of x and y in the Cartesian plane. The area of an Argand diagram is called the complex plane by mathematicians. The study guide, Basics of Complex Numbers, describes the Cartesian form of a complex number z as z equals a plus bi. Cartesian form of a complex number, where a is the real part of a complex number, written re of z, and b is the imaginary part of a complex number, written im of z. In an Argand diagram, the horizontal axis defines the real part of the complex number, and the vertical axis defines the imaginary part. A complex number in Cartesian form has the coordinates AB in an Argand diagram. A purely real number is positioned on the horizontal axis of an Argand diagram, and a purely imaginary number is a position on the vertical axis of an Argand diagram. Example. Represent the complex number z equals 5 plus 3i on an Argand diagram. Firstly, let's draw the real and imaginary axes. Marking 5 on the real axis, as 5 is the real part of z, and 3 on the imaginary axis, as 3 is the imaginary part of z. The position of the number z equals 5 plus 3i is shown as an x, but the number itself is usually represented as a line from the origin to the point. You should label the horizontal axis as re of z and the vertical axis as im of z in an Argand diagram. The modulus and argument of a complex number. As soon as you represent a complex number visually, you can begin to explore other ways of describing it. For example, an Argand diagram shows the similarity of a complex number with a vector. You can think of re of z and im of z being the number of steps along the real and imaginary axes, respectively, required to reach z. You can also get to z in a straight line directly from the origin. In order to do this, all you need to know is what direction to face and how far to go. How far you need to go is the length of the line representing the complex number in an Argand diagram, and is called the modulus of the complex number. It is very common to represent the modulus as a complex number z by the symbol this, which is a z between two horizontal bars, or simply by the letter r. The value of the modulus is always positive. You can use Pythagoras Theorem to find the modulus of a complex number. See study guide, Pythagoras Theorem. Below, the Argand diagram given for z equals 5 plus 3i from previously in the guide has been annotated to reveal a right-angled triangle. As you can see, the modulus of the complex number is the hypotenuse of the right-angled triangle. Using Pythagoras' theorem, the modulus of z squared equals r squared, which equals 5 squared, plus 3 squared, which equals 34. So, the modulus of z equals r, which equals the square root of 34, taking the positive root. The modulus of a general complex number written in Cartesian form as z equals a plus bi is the modulus of z equals r equals the square root of a squared plus b squared. Example, find the modulus of the following complex numbers. A. Z equals minus 2 minus I. Here, A equals minus 2 and B equals minus 1, and so the magnitude of Z equals the square root of minus 2 squared plus minus 1 squared, which equals the square root of 5. B. Z equals minus 6I. Here, A equals 0 as there is no real part, and B equals minus 6, and so the magnitude of Z equals the square root of 0 squared plus minus 6 squared, which equals 6. C. Z equals 3.4. Here, A equals 3.4 and B equals 0 as there is no complex part, and so the magnitude of Z equals the square root of 3.4 squared plus 0 squared, which equals 3.4. The modulus tells you how far to go from the origin to get to a complex number in an Argand diagram. You also need to know what direction the complex number is. This is known as the argument of a complex number, which is written as either arg of z or the Greek letter theta. Arguments are always measured in radians and take values in the range from minus pi to pi. Complex numbers either on the real axis or in the upper half of the complex plane have a positive argument measured anti-clockwise from the real axis. Complex numbers in the lower half of the complex plane have a negative argument measured clockwise from the real axis. You can use the inverse tangent or arctan function to find arguments. This can be confusing, and the table below is designed to help you. It is a very good idea to sketch your complex number before trying to calculate its argument. For complex numbers in quadrant 1, a sketch of the Argand diagram would look like this. The real part of the complex number a is positive. The imaginary part of the complex number is positive. And the argument is positive. You can use the formula theta equals the inverse tan of b over a to work out the argument. For quadrant 2, with an Argand diagram sketch like this, the real part of the complex number a is negative, the imaginary part of the complex number b is positive, the argument is positive. You can use the formula theta equals pi plus the inverse tan of b over a to calculate the argument. For quadrant 3, shaded in the diagram to the right, the real part of the complex number a is negative, the imaginary part of the complex number b is also negative, and the argument is negative. You can use the formula theta equals minus pi plus the inverse tan of b over a to calculate the argument. Finally, in quadrant 4, shaded in the diagram to the right, the real part of the complex number a is positive, the imaginary part of the complex number b is negative, and the argument is negative. You can use the formula theta equals the inverse tangent of b over a to calculate the argument. The real axis is part of quadrants 1 and 2, not quadrants 3 and 4. Given this, positive real numbers are in quadrant 1 and have an argument of 0. Negative real numbers are in quadrant 2 and have an argument of pi. Also, the argument of a purely imaginary number above the real axis, positive b, is pi over 2. The argument of a purely imaginary number below the real axis, negative b, is negative pi over 2. Example, find the modulus of the following complex numbers. A. Z equals 5 plus 3i. As you can see, Z equals 5 plus 3i is in quadrant 1. Also, the real part of Z equals A, which equals 5, and the imaginary part of Z equals B, which equals 3. Using the appropriate formula from the table, theta equals the inverse tangent of B over A, which equals the inverse tangent of 3 over 5, which equals 0.54 to 2 decimal places. So, for Z equals 5 plus 3i, theta, or the argument of Z, equals 0.54 radians. B. Z equals minus 2 minus I. As you can see, Z equals minus 2 minus I is in quadrant 3. Also, the real part of Z, which equals A, equals minus 2, and the imaginary part of Z, which equals B, equals minus 1. Using the appropriate formula from the table, theta equals minus pi plus the inverse tan of B over A, which equals minus pi plus the inverse tan of minus 1 divided by minus 2, which equals minus 2.68 to 2 decimal places. So, for Z equals minus 2 minus I, theta, or the argument of Z, equals minus 2.68 radians. C. Z equals minus 6i. As you can see, Z equals minus 6i is a purely imaginary number below the real axis, with the real part of Z equals A equals 0, and the imaginary part of Z, or B, equal to minus 6. This means that theta, or the argument of Z, equals minus pi over 2, as Z equals minus 6i is at a right angle to the real axis. D. Z equals 3.4. As you can see, Z equals 3.4 is a positive, purely real number, with the real part of Z, or A, equal to 3.4, and the imaginary part of Z, or B, equal to 0. Positive real numbers are defined as being in quadrant 1. This means that theta, or the argument of Z, equals 0. Polar form of a complex number. As you have seen, a complex number can be defined not only in terms of its real and imaginary parts, but also in terms of its modulus and argument. Just as the Cartesian form of a complex number uses the real part of Z and the imaginary part of Z, there is another way of writing a complex number which uses the magnitude of Z and the argument of Z, called the polar form. By definition, the polar form of a complex number is Z equals R multiplied by e to the power I theta, where R is the modulus and theta is the argument of Z. Here e is the base of natural logarithm. See study guide Exponential Functions for more details. The derivation of this form of a complex number is beyond the scope of this guide, but a learning enhancement tutor will happily explain it to you. The polar form is simply another way of writing a complex number, and you need to be comfortable converting from Cartesian form to polar form and vice versa. The previous sections have shown you how to calculate the modulus and argument of a complex number if you know the real and imaginary parts, and so you can use those methods to help you convert a complex number from Cartesian to polar form. Example: write the following complex numbers in polar form. A. Z equals 5 plus 3i. B. Z equals minus 2 minus I. C. Z equals minus 6i. And D. Z equals 3.4. You can use the results from earlier in this guide to work out the polar form. A. For Z equals 5 plus 3i, r equals the square root of 34, and theta equals 0.54 radians. And so the polar form is Z equals the square root of 34 multiplied by e to the power 0.54i. B. For Z equals minus 2 minus I, r equals the square root of 5, and theta equals minus 2.68 radians. And so the polar form of Z is Z equals the square root of 5 multiplied by e to the power minus 2.68i. C. For Z equals minus 6i, r equals 6, and theta equals minus pi over 2. And so the polar form is Z equals 6 multiplied by e to the power minus pi over 2i. For Z equals 3.4, r equals 3.4, and theta equals 0. And so the polar form is Z equals 3.4 multiplied by e to the power 0, which equals 3.4, as any number to the power 0 is equal to 1. You now need to know how to convert a complex number in polar form to Cartesian form. To do this, you also use trigonometry. Look at the Argand diagram below. You can use trigonometric ratios to find a and b in terms of r and theta, as you have a right-angled triangle. Here, the real part of z equals a, which equals r multiplied by the cosine of theta. And the imaginary part of z, which equals b, equals r multiplied by the sine of theta. And so you can write the Cartesian form of a complex number as z equals r cos theta plus r sine theta multiplied by I. This is an important result that links complex numbers and trigonometry. You can read the study guide, Trigonometric Ratios, Sine, Cosine and Tangent for more details about the definition of sine and cosine in a right-angled triangle. Example: write the following complex numbers in Cartesian form. A. For z equals 2 multiplied by e to the power 1.2i, r equals 2, and theta equals 1.2. To convert to Cartesian form, use the real part of z, which equals a, equals r cos theta. So, using radians, a equals 2 multiplied by the cosine of 1.2, which equals 0.72 to 2 decimal places. For the imaginary part of z, which equals b, it equals r multiplied by the sine of theta. So, using radians, b equals 2 multiplied by the sine of 1.2, which equals 1.86 to 2 decimal places. So the Cartesian form of z equals 2 multiplied by e to the power 1.2i is z equals 0.72 plus 1.86i. For z equals the square root of 3 multiplied by e to the power minus 1.4i, r equals the square root of 3, and theta equals minus 1.4. To convert to Cartesian form, use the real part of z, which equals a, equals r multiplied by the cosine of theta. So, using radians, a equals the square root of 3 multiplied by the cosine of minus 1.4, which equals 0.29, to 2 decimal places. The imaginary part of z, which equals b, equals r multiplied by the sine of theta. So, using radians, b equals the square root of 3 multiplied by the sine of minus 1.4, which equals minus 1.71 to 2 decimal places. So, the Cartesian form of z equals the square root of 3 multiplied by e to the power minus 1.4i is z equals 0.29 minus 1.71i. C. For z equals e to the power I pi, r equals 1 and theta equals pi. To convert to Cartesian form, use the real part of z equals a, which equals r cos theta, and so a equals cos of pi, which equals minus 1. The imaginary part of z, which equals b, equals r multiplied by the sine of theta, and so b equals the sine of pi, which equals 0. So the Cartesian form of z equals e to the power I pi is z equals minus 1. This is an important result and is discussed in the study guide, Euler's identity and de Moivre's theorem. Further guidance and information. If you have any further questions about this topic or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk, or you can visit our website www.uea.ac.uk/dos/let. There are further resources on many other aspects of mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.